Okay, oops. Let's get started. All right, answer your names, please. Okay. Laurent, here. Bessie, Bert. Check out mine here. Kane is here. Dunlap, Gallegos, here. Head, here. Irvin, Leonard, Medina Kylie, Medina Manuel, here. Minisi, here. Monsieur, Olano, Jasmine Richardson, here. Sieg is here. Tillman, Venture Pagada, here. Weflin, and Wright. All right. So we're going to continue our discussion of acids and bases. And now we're going to discuss how do we determine or calculate the pH of weak acids, because the last time we were here, we discussed how to determine the pH of strong acids and also strong bases, right? And if you remember, we said that the thing about strong acids and strong bases is that they undergo complete dissociation, and that makes things a bit easier for us in terms of calculating the pH, right? We can assume 100% dissociation, and therefore, based on the amount of the concentration of the strong acid or strong base, we can determine the concentration of H plus and OH minus directly, and therefore, based on those numbers, we can determine the pH of the acid or base. Now, what you're going to find is that in the case of weak acids and weak bases, it's a bit more complicated, and the reason why is because it's not going to dissociate 100%, so we can't make the same assumption that we made for strong acids in the case of weak acids, and the same is true for weak bases, all right? So let's talk about what is called the ionization constant, which will be very important for us to determine the pH of a solution. So in the case of a weak acid, as I said before, it's not 100% dissociation, so you're going to have a back and forth. Equilibrium will be established eventually, and therefore the concentrations of everything here will be constant. Of course, because the acid is weak, the concentration of HA you'd expect to be higher compared to the concentration of the hydronium ion or the A- ion, the conjugate base of the weak acid. Another way of representing it is this, right? So you can use this equation here or this equation. Basically, they both represent the same thing, the dissociation of the weak acid. Now, because the system, in either case, is in equilibrium, we can write down an equilibrium expression. And, it's basically similar to Kc. So if we're going to use this equation here, we're going to have the equilibrium constant here called Ka, and that will be equal to the product of the concentration of H plus and A minus divided by the equilibrium concentration of HA, right? And there's a special name given to this constant, Ka. It's called the acid ionization constant. In some textbooks, they call it the acid dissociation constant, all right? So that's Ka, that's the equilibrium constant for this system right here, all right? And what you'll find is that as the Ka increases, then the strength of the acid will increase, right? So we can use Ka in terms of comparing the acidities of, two weak acids. So if one weak acid has a higher Ka value than another, then that weak acid with a higher Ka value would be stronger, right? So the Ka is basically, the magnitude of Ka is basically a reflection of the strength of the weak acid. And here we have in this table some selective or selected weak acids. For example, hydrofluoric acid, its Ka value is 7.1 times 10 to the minus 4. And we have down here ascorbic acid, which is the same thing as vitamin C. Its Ka value is given right here. Acetic acid has a Ka value of 1.8 times 10 to the minus 5, and so on, all right? Now, let's not pay attention to the right side of the column quite yet, all right? I just want us to focus on the Ka value. And pretty much all I'm going to say here is reiterate what I said earlier. The higher the Ka value in terms of magnitude, then the stronger would be the acidity of that particular acid. So for example, if you compare these two, hydrofluoric acid and nitrous acid, you'll see that hydrofluoric acid has a Ka value which is higher compared to the Ka value of nitrous acid, and therefore we can conclude that hydrofluoric acid is a stronger acid. Okay, so how do we calculate the pH of a weak acid? So that's what this example is all about. Question is asking what's the pH of a 0.5 m solution of hydrofluoric acid. So the first thing I'll do is write down the equation for the dissociation. And of course, the Ka expression is given right here, which is equal to 7.1 times 10 to the minus 4. And let me just say that there are tables that have been put together for the Ka values of different weak acids. In fact, we have a table, or I have posted a table in Canvas. Let me just show you what it looks like. Files, and then tables, dissociation constant. Okay, so this is the table right here. Okay, so this is the table I'm referring to that you will have access to during your test, all right? So you'll be provided this table, and this is a more comprehensive list of different weak acids and their corresponding Ka values, right? Let me just say here that you see that there are some weak acids that have more than one Ka value, right? So the first one is called Ka1, then Ka2, or Ka3. So for example, in the case of an acid I talked about last time, sulfuric acid, right? Where is it? Sulfuric. Okay, so in the case of sulfuric acid right here, if you remember I said that sulfuric acid is kind of different compared to the other strong acids, where the first release of the hydrogen ion is strong, and then the second release is weak, right? And that is reflected in the Ka values for sulfuric acid. So this is H2SO4. The first Ka value is large, which means that the release of the first hydrogen ion is a strong unidirectional process, right? And then now to remove or release the other hydrogen ion or proton, then that is not as strong, and therefore the Ka value for that, which is called the Ka2 value, is equal to 1.2 times 10 to the minus 2, all right? So basically, you can have more than one release of protons for some acids, and therefore, correspondingly, you have different Ka values for each release, all right? Okay, so that's a table that you're gonna have access to. So let me go back to the PowerPoint here, and we're going to solve this example. So this is the dissociation equation, and this is the Ka expression. So what we're going to do is set up a nice table, similar to the ones that we dealt with before. Initially, the concentration of HF is going to be 0.5. Oops, sorry. So the concentration of HF is 0.5. And the concentrations of H plus and F minus would be 0 and 0. Now, we don't know what the change is as the system moves towards equilibrium. So we're going to say let X represent the amount of HF that is reacting, right? So the change in the concentration of HF would be minus X, which means, based on the stoichiometry of the of the dissociation of the weak acid, the change in the concentration of H would be plus X, and the same would be true for F minus, right? Because of the 1-to-1-to-1 mole ratio between the amount of HF reacting and the amount of H plus and F minus that is produced, right? So to get the equilibrium terms, all we have to do is add the first to the second line of values, and this is what we're going to end up with. For the HF, we're going to end up with 0.50 minus X, and for the H plus and the F minus, you're going to end up with X, all right? So we can basically plug these terms into this equation, and this is what you're going to get. You're going to get S squared over 0.50 minus X being set to be equal to 7.1 times 10 to the minus 4. And from here, of course, we have to do some algebraic changes in order to get the solution for X. Now, what you can do, and what I would recommend you do when solving this problem, is to make an assumption, right? Or problems of this type. You're going to make an assumption. And the assumption is, because Ka is a very low number compared to 1, that means that the X value will be very small. And what that means is that the X value will be so small that 0.50 minus X will be approximately equal to 0.50. So because it's a weak acid, that means that you'd expect that the X value will be small compared to 0.50, such that 0.50 minus X is approximately equal to 0.50. And that simplifies things a bit, because basically what that means is that you're going to end up with 0.50 alone here, because the X will be dropped. And therefore, when you solve for X, all you have to do is cross multiply by 0.5 and then find the square root, and you're going to end up with X being equal to 0.019. Now, we're not finished yet, because the question is asking for the pH of the solution. And you should remember that the pH by definition is what? What's the definition of pH? Minus log of?
Concentration of H plus.
Concentration of H plus. So X here is the concentration of H plus. We just solved for X right here. So therefore, we can basically find the pH by using the equation that she just mentioned, right? pH is equal to minus log of the concentration of H plus. In this case, the H plus would be 0.019, and it turns out that the pH of this solution is going to be 1.72. All right? So that's how you do that. Now, that's not the end of the story, because remember, we made an assumption earlier, right? The assumption is that X is small, such that 0.50 minus X is approximately equal to 0.50. What we have to do is to see whether or not that approximation is a valid one. And the criteria that we use to determine whether or not the approximation is valid is that we determine what is known as the percent dissociation. And I think I need to define it. So let me do some scribblings here. So let me just squeeze it over here. Let me just draw this line here. Percent dissociation of an acid, and there's a similar expression for bases. That would be equal to the concentration of H3O plus or H plus. Let me use H plus, since that's what we've been using all along. The concentration of H plus at equilibrium divided by the initial concentration of HA times 100%, right? So we call that the percent dissociation, right? That is equal to the concentration of H plus at equilibrium divided by the concentration of HA initially, and we multiply that by 100%. And that will give you the percent dissociation, right? So basically, whenever you do a problem of this type, after you have made the approximation, you have to test to see whether or not the approximation is valid. And the way we test it is in this statement right here. When the percent dissociation is less than 5%, then basically the approximation would be valid. So basically, we're going to calculate the percent dissociation right here. This is the concentration of H plus at equilibrium. This is the initial concentration of the acid times 100%, and it turns out that that works out to be equal to 3.8%, which is obviously less than 5%. So therefore, because of that, we can come to the conclusion that because the percent dissociation is less than 5%, that means that the approximation is okay, and therefore the calculation of the pH based on that is okay as well. all right? So that is something that you have to do whenever you're doing calculations of this type. And later on, I'm going to show you how to deal with it when the approximation is greater than 5%, right? So we'll talk about that later on, all right? So let's look at this example right here. What is the pH of a 0.05 molar HF solution of, solution of hydrofluoric acid? And basically you do the same thing, right? Just as you did before. You do your ice table and then you make your approximation. And this time you're going to end up with this expression, x squared is equal to, s squared divided by 0.05 is equal to 7.1 times 10 to the minus 4. So when you do your rearrangement to solve for x, it turns out that x is equal to 0.06, right? M. Now, if you were to find the percent dissociation based on that, you're going to see that the percent dissociation is 12%, right? Which obviously is greater than 5%, all right? So what does that mean? That means that the approximation that you'd have made earlier would not be okay. And therefore, you'd have to go a longer route in terms of solving for x. So we're going to get into another example where I'm going to show you exactly how that is done, all right? Okay, let me see here. Let me see. Oh, I just remembered, there's some questions that we have not touched yet from last time. Well, let me just check something here. I should have started with that first. Okay, let me continue and then we'll get to the assignment question, right? So just to reiterate what I just said, if the percent dissociation, and in some textbooks they call it the percent ionization, same thing. If the percent dissociation or ionization is more than 5%, then basically the approximation is not okay. And as stated down here, you need to solve for x exactly using the quadratic equation or method of successive approximation. Okay, which we won't be dealing with. All right, so let's move on to, so here's the definition of percent dissociation or percent ionization. I gave you basically the same definition. So this is the same thing. This is the ionized acid concentration at equilibrium, which would be the concentration of H plus divided by the initial concentration of the acid times 100%. And what you're going to find is that in the case of weak acid, right, as you increase the initial concentration of the acid, what you'll find is that the percent ionization will decrease, all right? For strong acids, the percent ionization will be 100% regardless of what the concentration of the acid is, all right? But in the case of weak acid, you'll find that there's a drop-off in terms of the percent ionization as the solution becomes more and more concentrated. Okay, so let me see here. Okay, so this is the equation which I showed you earlier for calculating the percent ionization or dissociation of an acid. It's a concentration of H plus at equilibrium divided by the initial concentration of the acid times 100%, all right? Okay, so let's talk about the steps involving solution of problems dealing with weak acids, right? First, you identify the major species that can affect the pH, which of course would be the acid or the base, which we'll talk about later on. In most cases, you can ignore the contribution of H plus from the auto-ionization of water. And similarly, you can ignore the concentration of OH minus because it is determined by the concentration of H plus. And just to remind you, the relationship between the OH minus concentration and H plus is concentration of OH minus times the concentration of H plus is equal to Kw, all right? So basically, if you can determine, or if you're given the H plus, you can determine the concentration of OH and vice versa because Kw is equal to 1.0 times 10 to the minus 40, all right? Okay, so basically, in order to solve problems like these, we take the same approach as we did initially. we use the ICE table to basically determine the expressions for the equilibrium concentrations. And then you plug those values or those terms into the Ka expression, and then you solve for X if the approximation, the 5% criteria, is not met by the dissociation of the weak acid, all right? And basically, based on X that you're gonna get, and based on the question that you're asked, for example, you might be asked for the pH, then X would give you the concentration of H plus, which you can use to find the pH, or the question could ask you to calculate the concentrations of everything present at equilibrium, and you can determine that based on the terms which contains X in the ICE table. All you have to do is plug the values for X that you would have determined into those terms, and that will give you the concentrations of the different terms, all right? Or the different components in the system. Okay, so here is an example which I think involves one where the percent ionization is greater than 5%. So they gave you the concentration of some monoprotic acid and they gave you the Ka value, right? So you write the equilibrium expression for that acid and you set up your ICE table, initial change and equilibrium. So the initial concentration of the HA would be 0.122 m. The initial concentration of H plus and A minus would be 0. Again, we don't know what the amount of HA reacting is, so we're going to call that X. So the change in concentration for HA would be minus X, and the change in the concentration of H plus and A minus would be plus X each. And then we write down the terms for the equilibrium concentration, which of course would be the sum of the first line with the second line, and this is what you're going to end up with. And then we write down the Ka expression and plug these terms into the Ka expression, and this is what you're going to end up with. And then now we made the approximation that X is small compared to 0.122. When we do that and solve for X, this is what we end up with. X equals to 0.0083. And then when we try to find the percent dissociation of the acid, we divide the X value, which would be the equilibrium concentration of H plus, by the initial concentration of HA. And what do we see here? We get a value of 6.8%, which obviously would be greater than 5%. So therefore, the approximation that we made earlier would not be acceptable. So therefore, what does that mean? That means we have to come back to this equation here and solve it the longer way. So on the next slide, that's what we're going to start off with right here, right? So again, like we did in previous problems, we have to do some algebraic manipulation. So after a couple of steps, I won't show you all the steps, you're going to end up with this quadratic equation, right? And then when you solve for this quadratic equation, using, of course, the quadratic formula, then you're going to end up with two values of X, right? And guess which one would be the right one? The positive one, right? Because you can't have a negative concentration, right? So this is X that we're going to use, and that X basically would be equal to the concentration of H plus and the concentration of A minus, right? So that's what we're going to have here. And then we can find the pH. pH would be minus log of that value. And it turns out to be equal to 2.09, right? And I think that's it as far as answering that question is concerned, all right? So this is a typical approach that you'll take into solving problems where you're asked for the pH of a weak acid. Any questions about this? Any questions? Any questions? Yes, sir.
Does that formula AX squared plus BX plus C turn into the one on the right? X equals?
Yes.
Okay.
So the A would be 1, the B would be 0.0057, and the C would be minus 6.95 times 10 to the minus 5. And then you solve for that to get X. Yes, sir.
You try to get the approximation of X again.
I'm sorry?
The approximation of X.
The
Approximation of X. The 8. It was like 0.0083.
Oh, yeah. That's when you assume that X is much less than 0.122, such that that would be equal to 0.122. So basically, you're going to end up with 0.122 here without the X. And then you solve for X, and that gives you 0.0083. All right? Now, let me just say something here, which I probably should have told you from before. Because of the fact that when you encounter problems like this, you might have to solve a quadratic equation. For my classes, when I teach Gen Chem 2, I will allow my students to use those fancy calculators you guys have, the TI, I think it's called 83. You can program those calculators so that it can solve quadratic equations such as this one. All you have to do is enter the A value, the B value, and the C value, and I think you press execute, and it gives you the two X values, and that's it, right? So I have no problem with you guys doing that. And if you don't know how to do it, I think I have posted a YouTube video in Canvas. Let me see if it's still there. I remember I deleted a couple of stuff, so I don't know if I deleted that. I think it's in the announcement section. Okay, here it is. So this is the link right here, and there's a YouTube video. So if you have that type of calculator, you may want to check that out so you learn how to program it so that you don't have to be using the quadratic formula, especially during test time, right? So I would strongly recommend that you do that. All right, so let me go back to the PowerPoint here. Let me see here. Okay, when it comes to weak bases, very similar approach to what we did with weak acids, right? And also, let me go back to this here. Well, all right, sorry. Let me just continue with this, and then I'll show you what I intend to show you. Okay, so for weak bases, and I'm going to use ammonia as an example, right? So this is how ammonia reacts with water to form ammonium and OH minus, right? So we can write down an equilibrium expression for the dissociation of the weak base, and the equilibrium constant in this case is called the base dissociation or ionization constant, right? Kb, right? So Kb is equal to NH4 plus times the concentration of OH minus divided by the concentration of the ammonia based on this equation right here, right? So that's called the base ionization constant. And in the case of Kb will increase with increasing base strength, right? So just as we said in the case of weak acids, that the stronger the acid, the greater will be the Ka value. The same or the similar is true for the base, weak base. The stronger the weak base, the greater will be the Kb value. So you can make comparisons between two weak bases. The one with the higher Kb value would be the stronger weak base, all right? So when it comes to solving problems involving weak bases in water, like for example, determining the pH or concentrations of the different components in the system, you go about it pretty much in a similar fashion to what I just showed you, with one difference. The X that you'd solve in this particular case would be equal to the concentration of the OH minus, right? And therefore, to find the pH, you have to first find the POH, right? And then subtract that value from 14 to get the pH. So there are like two extra steps involved when it comes to determining the pH of a solution of a weak base. And I think one of the questions in the assignment will be with that. So you're going to see how that works, all right? So that's basically the introduction to the base ionization constant. And these are different bases and their corresponding Kb values, all right? So this is ethylamine. Most weak bases are organic in nature. So that's why you see all these compounds here. The only one that's not organic is ammonia, but all these other bases are weak bases. And another thing I should say too is that most weak bases are contain nitrogen, right? If you look at this carefully, these are weak bases that contain nitrogen, including some naturally occurring compounds like caffeine, right? Caffeine, which you can find, of course, in coffee, and urea, which you can find in the urine of mammals, all right? So those are some weak bases. And as you can see, the Kb values are relatively small because the bases are weak. Okay, all right, so before we get into the ionization constants for conjugate acids base pairs, I think the last question we did, can somebody remind me, but I think it's question 7, right? In the assignment, question 7. At least that's my recollection. Let me bring that up. Okay, so let me go down. Okay, so I think question 7 was the last question we did. So let's move on to question number 6. So question number 6 says you have an acidic solution that has a pH of 4. If I dilute 10 mils of the solution to a final volume of 1,000 mils, what is the pH of the resulting solution? All right. So let me hear your suggestions as to what we should do to solve this problem. Let me turn on my pen here. Okay, so any ideas? They gave you the pH, they gave you the initial pH, right? And then you're diluting 10 mils of solution to a final volume of 1,000 mils, right? So the question is asking what would be the final pH of the resulting solution? So any ideas?
Would you add the 1,010 together?
Nope. Remember, you're diluting. So therefore, you're adding water until it gets to 1,000 mils. You're not adding 1,000 mils to 10 mils. All right, so you're diluting to a final volume as worded here, 1,000 mils. So let me hear what you guys have to say. What would be your first step in this process?
For milliliters to liters.
Don't need to do that. You can do that. Well, firstly, that wouldn't be my first step, but you could do that later on, but it won't make a difference. You're adding extra steps to solving a problem which is not necessary. Yes, sir.
You find the molarity of H plus.
Very good. You're going to find the initial molarity of the H plus. How would you do that? So let me write this down. Initial concentration of H plus. How would you find that?
Plus equals 10 to the power of negative pH.
Okay, so the pH is 4, so that would be 10 to the minus 4, right? So therefore, this would be the initial molarity of the H plus. Okay, very good. Very important first step. What next? Now that we have the initial concentration of H plus, what would be your next step?
Plug it into the pH.
I'm sorry?
You plug it into the pH.
No, not yet. Because remember, the pH is the initial pH. The 4 is the initial pH, right? And as he said, you calculate first the concentration of H plus. Then you're going to dilute it to 1,000 mils, right? Well, what's the exact equation you're going to use to find the final concentration of H plus? Yes, sir.
M1 V1 equals M2 V2.
Exactly. M1 V1 is equal to M2 V2. Remember that equation from Chem 1, right? The dilution equation. So M1 would be the initial molarity, which is this. V1 would be the initial volume, which is this. M2 is what you're trying to get, and V2 would be the final volume, right? So this is this would be M1, this would be V1, and this would be V2, right? So how do we get M2? M2 would be equal to what? If this is true, what is M2 equal to? M1 times
V1
V1 divided by
V2.
V2, exactly. So that's what you're going to find here. M1 is 10 to the minus 4, M times V1, which is 10 mils, divided by V2, which is 1,000 mils. And when I did that calculation, I got 1 times 10 to the minus 6, or simply 10 to the minus 6, M. This will cancel out with that. So that will be the final concentration of H plus. But we're not finished yet because the question is asking for the final pH. So how do we find the final pH?
Negative log of
Minus log of
10 to the 6th.
10 to the minus 6. And that would be equal to 6. And that's how you do that. Excuse me. All right. Any questions? Okay, so moving along. Question number 7. Is it okay for me to clear this? All right. So scrolling down to number 7. All right. Determine the pH of the following solutions. Let's start with the first one. How would you determine the pH of that solution? First thing you should ask is what? Remember what I told you yesterday? When you're asked to calculate the pH of any acid solution, what's the first thing you ask yourself?
It's a strong acid or weak.
Exactly. And remember I told you, you need to memorize 6 strong acids. Can anybody tell me what they are? I'm sorry?
HBr,
HBr,
HI,
HI,
HCl.
HNO3, HCl, perchloric,
H,
and
SO2.
sulfuric, right? You need to remember those 6 acids, right, as strong acids. Pretty much all other acids you'll be given are weak acids. So we identified correctly that HBr is a strong acid. So what's the next step? What's the next step? Because HBr is a strong acid, what does that mean? It undergoes complete dissociation. So therefore, whatever the concentration of this is, the concentration of H plus is going to be the same. So the concentration of H plus is going to be equal to 4.5 times 10 to the minus 3 M. So what next? How do we find the pH?
Negative log,
Minus log of 4.5 times 10 to the minus 3 M. And then we do the calculation. So remember, whatever the number of sig figs that you find the log of, you have to round off that answer to the same number of decimal places. So 4.5, 4.5 times 10 to the minus 3. And then I'm going to divide that, not divide, I'm sorry. 4.5 times 10 to the minus 3. I'm going to find the log of that, minus sign. So this, according to my calculation, works out to be equal to 2.35. And that would be the answer. All right? Okay, any questions about that one? Any questions? Any questions? Okay. B, 3.67 times 10 to the minus 5 M, potassium hydroxide solution. All right? So how would you solve that? Again, you have to ask yourself the question, is this a strong base or weak base? And I don't remember if I told you this, but as far as strong bases are concerned, all you have to remember are the hydroxides of groups 1A and 2A. If you're in my Chem 1 class, you should know that, but I don't see anybody else in my who was in my Chem 1 class. So I won't reprimand you about that. So basically, all hydroxides in group 1A, all metal hydroxides of 1A and 2A metals can be considered to be strong bases, right? So that's easy to remember. All you have to do is consult the periodic table and that's it. Pretty much all other bases are weak, and that includes the organic bases that I showed you earlier, like caffeine and all that, right? So based on what I just said, potassium hydroxide would be a strong base, which means it will undergo complete dissociation. So what does that mean? If it undergoes complete dissociation, that means that the concentration of OH minus is what?
3.67 times 10 to the negative 5.
Exactly. So what would you do next to find the POH? I'm sorry, I gave the hint away already. Okay, what would you do to find the pH? I just gave the hint away.
Minus log of 0.67 times 10 to the negative 5
Minus log of
for OH.
3.67 times 10 to the minus 5, and that's a POH. Okay, but the question is asking for the pH. So let me work this out first. So 3.67 times 10 to the minus 5, and then I find the log of that and then put a minus in front of that. So 4.44 is a POH, but the question is asking for the pH. So yes, ma'am.
14.
Exactly. So the pH would be equal to 14.00 minus 4.44. And according to my calculations, this works out to be equal to 9.56. And that's how you do that. Yes, sir.
You not do the thing if it's 3 sig figs for POH that has 3 decimals.
Oh, yeah, you're right. So that means, let me go back to.
Where did 14 come from? Right.
So this should actually be 3.5, which means that I need to correct this as well. So this would be 3.5. And then when I subtract that from 14, I'm going to get 9. Well, in this case, so in this case, you have 2 decimal places subtracting 3 decimal places. So the final answer here would be 2 decimal places. So the answer still remains the same. I got 9.56 as the final answer. So the answer doesn't change, but you're right about, the significant figures. You have to notice that.
You not round up.
Huh?
You not round up if it's 9.565.
I got 9.5646. So the 4 after the 6 is less than 5. So you drop that digit and all digits afterwards. So that's what I got.
Where did the 14 come from?
Oh, you weren't here. 14 comes from this relationship. pH plus POH
Oh,
is equal to 14.
the formula is this, okay, I know what you're talking about.
Mhm.
I got you now. All right, thank you.
All right, any other questions about this? Okay. Is it okay for me to clear this? Okay.
Can you explain the sig fig thing again?
Okay, so he corrected me because this is 3 sig figs here. So that means that when you find the log of the number, you should have 3 decimal places, right? And then when I subtract that value from 14, because you have 2 decimal places here and 3 decimal places here, this must be rounded out to 2 decimal places. All right? And therefore the answer is 9.56. Yes, sir.
Wouldn't it be? I think you already said this, but wouldn't it be 5.7? Because when you subtract it. Because
For which one?
the answer, because I think it's
For
9.565.
No, let me do this again. It's 1.4 minus 1.4 minus 4.435. Oh, okay. Yeah, you're right. So that would be, okay, I know what I did. I should have rounded off the answer on my calculator, which I did. So, yes, you're right. This should be 7. Here. Okay. Let me make a note of this here. All right. Any other questions? Okay, yeah,
So how do we know if it's a strong base again? What are you looking at on the periodic table?
yeah, all the hydroxides of groups 1 and 2A in the periodic table. So like sodium hydroxide, potassium hydroxide, barium hydroxide, and so on. All those metals in group 1A and 2A. If they're combined with hydroxide ions, then that combination is a strong base.
As in like the columns?
Yeah, the columns, right, in the periodic table. To the extreme left.
Yeah.
Groups 1A
1, 2.
and 2A, right. Okay, any other, yes, ma'am?
So whenever you have the strong acid, you're gonna end up with a pH, and whenever you have the strong base, you're gonna end up with an OH.
It depends on what the question is asking for, but the first thing you'll be able to find out in the case of strong acid will be pH, and the first thing you'll find out is the pOH for strong bases. But in this case here, because the question is asking for pH, then once you get a pOH for the strong base, you have to subtract that from 14. You could just as well be asked the pOH for the strong acid. You have to do the same thing. You have to subtract the pH from 14 to get a pOH for the strong acid. So it all depends on how the question is worded. All right?
So when you get the OH minus, that's when you do the POH first?
Exactly. If the question is asking for the pH, you find the pOH first, and then you subtract it from 14.00, and that will give you the resulting pH.
Okay.
Yeah. Okay, any other questions about this? So let's clear this and move on to the C part, which says you're to find the pH of a solution by diluting 25 mils of a 6.0 m hydrochloric acid until the final volume is 1.75 liters. So let me hear your suggestions as to how to do this one. They gave you the initial volume, they gave you the initial concentration, and they gave you the final volume.
Did you
Dilution.
You have to use the dilution, right? So this is V1, this is C1, this is V2, right? So how would you,
I have a question.
Yeah.
Since one of the units for volume is in milliliters, do you recommend changing that to liter?
you have to change from either milliliters to liters or vice versa, right? Good recognition right there. Okay, so first step, what's the first step? Oh, well, you said the dilution, right? So tell me what to write down here. 6.0 m times
0.025.
0.025 liters divided by 1.75 liters. So what she did was to convert the 25 mils to liters, but you could just as well convert the 1.75 liters to milliliters. Same result, right? So let's see what this gives. 6 times 0.025 divided by 1.75. And according to my calculation, please tell me if I'm wrong, but I got 0.0857, and the units would be M. All right? In fact, we need to round this off to 2 sig figs. So erase that here and convert that 5 into a 6. All right? M. Okay, so now that we have that molarity, what will be the next step? Remember, the aim is to find the pH of the solution. By the way, what kind of acid is this? Strong acid. So that means that this will undergo complete dissociation, right?
So then 0.086 will be equal to the H plus.
Exactly. So that will be equal to the concentration of H plus. So therefore, how do we find the pH? Minus log of 0.086. So what does that give? 0.086 log minus. Okay, so according to my calculation, we'd have to round this off to 2 decimal places. So 1.07 is what I got. All right?
3.
No, we have 2 sig figs here. Right? So that means that this must be into 2 decimal places. All right? Okay, any other questions about this one? Any other questions? Any other questions? Yes, ma'am.
So for the sig figs, is it when it's a log, you do decimal places?
Whatever the number of sig figs that you're applying the log to, the
That's only
results
the-
must be rounded off to the same number of decimal places.
Of the log. Just for.
Right, exactly. So if the number, like in this case, you apply the log to a number which has two sig figs, that means that the result should have two decimal places. Right. Okay, any other questions about this one? Any other questions? Any other questions? Okay, moving on to D. This one says a 5 liter, let me clear this first. Let's scroll down. Okay, so this question says a 5 liter of an aqueous solution contains 1.0 grams of HBr and 1.0 grams of nitric acid. So we have to find the pH of that solution. Let me hear your ideas about this one.
Add the two together.
Yeah, but you have to do something first. Before you add anything together. Exactly, so let's do that. So in the case of the HBr, it's 1.0 grams of the HBr. We have to convert to moles, so 1 mole of HBr will go above. And we need to find the molar mass. And you all know how I roll.
80.98.
I trust the old molar mass calculator. Is what I'm going to use. It has never failed me yet. Okay, so HBr. Oops. Uppercase B, R. And let's see what this gives. So this gives 80.91, which I think I heard somebody say, right? So here we're going to put 80.91, all right? And hold on, let me get onto this here. Okay, so this would be 80.91 grams of HBr, right? And we need to do the same thing for the nitric acid, 1.0 grams of HNO3 multiplied by, 1 mole of HNO3 up top. And again, below the molar mass of HNO3. If I remember correctly, the molar mass of nitric acid is 63 point something. So let me HNO3. And let's see what this gives. Yes, 63.01 goes here. 63.01 grams of nitric acid is in 1 mole. All right, so let me go back to this. So we need to work out both of these. So let me start with the HBr, 1 divided by 80.91. So according to my calculation, this works out to be 0.01, how many sig figs? 2 sig figs, 0.012 moles. And then in the case of nitric acid, it's 1 divided by 63.01, 1 divided by 63.01. And according to my calculations, this is equal to 0.016 moles. So therefore, when you add these two together, 0.012 plus 0.016, that gives you 0.028 moles. And then what we do is find the molarity. By the way, because HBr and nitric acid are both strong acids, that means that whatever the total moles here, that would be equal to the moles of H plus. So the concentration of H plus would be equal to 0.028 moles divided by the volume, which is 5 liters. So divided by 5. And according to my calculation, you have to round this off to 1 sig fig because you have only 1 sig fig here. I got 5 times 10 to the minus 3 m, or moles per liter, right? And then we have to find the pH. And of course, we all know how to do that, right? pH is equal to what? Minus log of. Yeah, which is 5 times 10 to the minus 3 here. Oh, this should be 6 actually, not 5. My bad. All right, so 6 times 10 to the minus 3, and then I find the log of that, with a minus sign in front. And now we have to round this off to, this is 1 sig fig, so 1 decimal place, so 2.2 is what I got. And that's how that is done. All right? Any questions about this one? Any questions? Any questions? No questions? Okay, let me clear this and see what's further down. Okay, so now we're going to get into the weak acid topic that we talked about earlier. So this says, find the pH of a 0.065 solution of formic acid, and it says that the dissociation constant Ka for formic acid is 1.8 times 10 to the minus 4, all right? So if you remember what I mentioned earlier, let me get my pen working. The first step would be to, whenever you ask to find the pH of something, you have to ask yourself, is this a strong acid or a weak acid? Well, in this case, it's a weak acid, and we know that because it's not one of the strong acids that I told you about, but also the fact that there's a Ka value given. Whenever you're given a Ka value, then basically you can automatically assume that the acid is weak, especially when the Ka value is relatively small, as you can see here, right? So we know it's a weak acid, so I'm just going to use HA. The formula is not really important to solving this problem, so I'm just going to use HA to represent the weak acid. And of course, we can recognize that because it's a weak acid, this is what's going to happen, right? You're going to have equilibrium. The initial concentration, so basically we're going to get into the ICE table, which we talked about before. The initial concentration of the acid is 0.065. You're going to have 0 here and 0 here. The change will be minus X for the HA, plus X for the H plus X for the A minus. So at equilibrium, we add this line to this line, you're going to end up with 0.065 minus X for the HA. And here, we're going to have X and X here, all right? Now remember, Ka is equal to the concentration of H plus times the concentration of A minus divided by the concentration of HA, all right? So we can put the terms in. So this would be equal to X times X, which would be equal to X squared, divided by 0.065 minus X, and that would be equal to the Ka. Then we make an assumption, right? We assume that X is so small compared to 0.065 such that 0.065 minus X is equal to, or approximately equal to, 0.065. So therefore that simplifies things here. X squared over 0.065 is equal to Ka. So therefore X would be equal to the square root of Ka times 0.065. And then we plug in the Ka value, which is 1.8 times 1.8 times 10 to the minus 4 multiplied by 0.065. So let's work this out. 1.8 times 10 to the minus 4 times 0.065. And then we find the square root of that. So according to my calculations, we have to round this out to 2 sig figs. So this gives us 3.4 times 10 to the minus 3. All right. Now we have to test to see if this approximation that we made here is valid. So if you remember, the way we do that, as I mentioned earlier, we determine the percent dissociation, right? So because I'm going to need some space, I'm going to erase up here. So remember now, percent dissociation is equal to the concentration of H plus at equilibrium divided by the initial concentration of HA at equilibrium times 100%. So in this case, the concentration of H plus, which would be equal to X, is 3.4 times 10 to the minus 3 m divided by the initial concentration of the acid, which is 0.065 m times 100%. And let's see what this gives. Hopefully it will be less than 5%. 3.4 times 10 to the minus 3 divided by 0.065 times 100. And what do we see here? I got 5.2%. So what does that mean? That means what?
Much.
The approximation is not okay, right? The percentage dissociation is greater than 5%. Yes, ma'am.
What was the writing you put under the ice table? Not sure what it said.
Where?
Up top, percent dissociation,
You mean here?
concentration of
No.
pH.
Right here?
No, like right next to the what times 2.006.
Assumption.
Oh, assumption.
Why?
Oh,
Assume,
that.
assume,
Oh, okay.
Yeah, assume that, yeah, sorry for my chicken scratch. Assume that X is less than 0.065. That's what that's saying. Yeah, okay. So what does that mean? If the percent dissociation is, oh, I'm sorry, yes, ma'am.
Why does it have less than 5%?
Because less than 5%, basically, if you were to do, okay. Try to find the shortest way to explain this. If the percent dissociation based on what we have done so far is less than 5%, then if you don't make the approximation, it's going to be it's going to be the same number, whatever it is. But once the percentage dissociation gets above 5% when you make the approximation, when you go the longer route, you'll see that the answer is different from when you made the approximation. You see what I'm saying? I don't know if I'm explaining it.
Is that like the percent error?
Kind of like, yeah. The percent error is basically non-existent if the percent dissociation is less than 5% when you make that approximation. All right? But once it gets above 5%, then basically there's a difference between what you get when you make the approximation and what you get when you don't make the approximation. And when you don't make the approximation, that would be the more accurate value. All right? Okay, so that means that we have to go the longer route. In other words, we have to get to here, and this is equal to 1.8 times 10 to the minus 4. So basically, we have to solve this equation the longer way. So unfortunately, that's what happens. So let me just clear this here. And let me write down what I just circled, which was x squared over 0.065 minus x is equal to 1.8 times 10 to the minus 4, right? So algebra is involved. We cross multiply to get x squared is equal to 1.8 times 10 to the minus 4 multiplied by 0.065 minus x, and then we, what's the term they use in math? Distribute. So 1.8 times 10 to the minus 4, we're going to multiply that by 0.065, and this gives 1. We have to round off to 2 sig figs, so 1.2 times 10 to the minus 5, and then here we're going to get 1.8 minus 1.8 times 10 to the minus 4 times x, all right? And then we have to arrange this in the form of a quadratic equation. So that means that you're going to end up with x squared plus 1.8 times 10 to the minus 4x minus 1.2 times 10 to the minus 5, and that would be equal to 0. So this is the quadratic equation which you'd have to solve. Let me see what I did when I did that. So when I solve for x, again, as I said before, if you have your calculators, I can do this automatically by programming it. I have no problem with that. But when I did this, I got x equals to 0.0034 or minus 0.0036. And of course, the negative one we can ignore. So therefore, we're going to go with X equals to this. And therefore, X is equal to the concentration of H plus, 0.0034 M. So therefore, the pH is equal to minus log of 0.0034. And according to my calculations, again, correct me if I'm wrong, but I got 2.47. That's how that is done. All right. Any questions about this one? Any questions? Any questions? No questions?
That last step is only because it was not less than 5%, correct?
Right, exactly. If the percent dissociation was less than 5%, we would not need to go through all of this right here.
And
Right?
why are we going through all this again?
Because the percent dissociation was greater than 5%.
No, not in that sense, but like I'm not gonna ask it correctly, so it's fine.
You sure?
Yeah,
I mean, you can ask me later.
yeah.
Okay, okay, so let me, oh, yes, sir.
How do we rearrange the equation to get x squared plus 1.8 times x?
Okay, so basically what I did was, in order to get the 1.8 times 10 to the minus 4 on this side, I would have to add it to both sides. 1.8 times 10 to the minus 4x, right? And here I'd have to subtract. So this here would have to be added to this side as well. Right? Minus 4x. And then in the case of 1.2 times 10 to the minus 5, I'd have to subtract 1.2 times 10 to the minus 5 from both sides. Right? And the result would be this equation right here. And then you solve for x. Right? Okay, any other questions before I move on? Any other questions?
So what would we have done if the percentage was under 5%?
You won't have to do all this.
So
You
then I would
just
stop.
remember the approximation we made, right? I erased it, but the previous part that I did, right? And I found x equal to, I don't remember what it was. What was x? What was the x? When I made the approximation, what was the x value?
10 to the negative third.
3.4 times 10 to the negative 3, which by the way is the same thing as this. But anyway, right, but to answer your question, basically, once we divide that by the initial concentration of the acid, which is the percent ionization, in that case, it was, if I remember correctly, 5.2%.
Yes.
So therefore, it's greater than 5. So therefore, we can't use that approximation, therefore, and therefore we have to come back to this and solve it the way that I just showed you. All right? Yes, ma'am?
So if the X was still the same number, what was
Right.
different?
Nothing, not in this case. But whenever the percent dissociation is greater than 5, you have to go through this route because it may be different. You see what I'm saying? It just so happens in this case that with or without the approximation, it's the same in this case, but I can't guarantee that will be the case in all cases. All right?
So if it was less than 5, then you would plug in X.
Right, if it's less than 5%, then you don't need to do this. You just accept the value that we got before. But if it's greater than 5%,
Have to do.
you have to do that. Yes, sir.
What if it's exactly 5%?
It has to be less than 5%. So if it's 5% or greater, you have to go through this. All right? Okay, any other questions? Any other questions? Okay, so let me, whoops, why did I do that? Let me clear this and scroll down to see what else we can do, if anything. Okay, I'm gonna leave you guys to do question, let me see, 9A, 9B. Okay, 9A and 9B, I'm gonna leave you guys to do that. Basically, what they're asking for you to do is to compare the pH of, in this case, 0.10 M nitric acid and 0.10 M nitrous acid, right? So let me just give you a brief overview of what you're gonna do. Basically, you should recognize firstly that nitric acid is a strong acid. And therefore nitrous acid will be a weak acid. So what you're going to do is, based on what we have done before, calculate the pH of the strong acid, which is nitric acid, which is simpler because it undergoes complete dissociation. And then you do the same thing with the nitrous acid, but this time it's not as simple because you'd have to write down the ice table and go through the steps, the same steps that we went through before, right? And then you're going to compare the two values. And that's basically what you're going to do for 9A and for 9B, something similar. The only difference is now you're comparing potassium hydroxide to ammonium hydroxide. Again, in the case of potassium hydroxide, that's a strong base, so that's simple, relatively speaking. But for the case of ammonium hydroxide, you'd have to determine the pH going through the steps, ice table, all that good stuff, right? So I'm going to leave that for you to try on your own. If you have any questions, feel free to contact me, which, by the way, just reminded that I've decided that I'm going to be here tomorrow. I would say definitely between the hours of 9 and 11. I might come earlier, but definitely between the hours of 9 and 11. I'll be in my office if you have any questions, including if you have questions about these that I just said that you should try on your own, right? And so feel free to come by or call me or email me so we can set up a Zoom link and therefore we can communicate that way, all right? So try those questions. Let me see what's next. Okay, calculate the percent ionization of, and it gives you 0.0015 M acetic acid, and it gives you the Ka value, right? So in this particular case, again, I'm just going to use HA to represent the acid. The formula is not that important when it comes to these problems. All right, so initially, you're going to have 0.015. Here you're going to have 0, here you're going to have 0. The change is going to be minus X here, plus X here, plus X here. And then at equilibrium, you're going to have 0.015 minus X. Here you're going to have X, here you're going to have X. So Ka would be equal to the concentration of, the concentration of H plus times the concentration of A minus. So that would be equal to X squared up here, divided by 0.015 minus X. And that will equal to, well, let me do this first. So assume X is much less than 0.015. Therefore, 0.015 minus X is approximately 0.015. So therefore, this simplifies Ka to be equal to X squared over 0.015, which means that X is equal to Ka times 0.015. And Ka, of course, is 1.8 times 10 to the minus 5, which is given up here, multiplied by 0.015. So let me do that calculation. So 1.8 times 10 to the minus 5 times 0.015. So according to my calculations, I got, oh, wait a minute, square root. How can I forget that? So let me do the square root here. So when I did the square root, rounded off to 2 sig figs, I got 5.2 times 10 to the minus 4 M, right? So that would be equal to the concentration of H plus. So to find the percent ionization, that would be equal to the concentration of H plus, which is 5.2 times 10 to the minus 4 M divided by the initial concentration of the weak acid, 0.015 M, and multiply that by 100%. And according to my calculations, when I did that, 5.2 times 10 to the minus 4 divided by 0.015 times 100%. That is equal to, according to my calculations, 3.5%, which is less than 5%. So the approximation is okay. So that's the answer to this question, right? The percent ionization is 3.5%. All right? Okay, any questions about this? Any questions? No questions? Okay, moving on. Okay. Let me clear this. Go down. Okay, now in this case, they're asking for you to do the same thing for 0.20 m ammonium hydroxide or aqueous ammonia. Same thing, right? So let me start off by writing down the equation for the dissociation of ammonium hydroxide. There are a couple of ways you can express this. Doesn't matter which way. I'm going to write it this way. Another way of doing this is NH3 plus H2O to give NH4 plus OH minus. So that's another way of doing the same thing. All right, so I'm going to use this way, right? So I'm going to start us off and let me hear what you have to contribute in answering this question. So I'm going to start off with a nice table. So what am I going to put here? 0.20 m. What am I going to put here and here? Zeros. Okay, very good. Here, I'm going to put what? Minus x. Here, I'm going to put plus x. And here, I'm going to put plus x. So down here, I'm going to have 0.20 minus x. Here, you're going to have x and x. So because this is a base, we have to write down a Kb expression, not Ka, but Kb. Kb would be equal to the concentration of NH4 plus times the concentration of OH minus divided by the concentration of NH4OH. Okay, so what are we going to put in the denominator here? I'm sorry, the numerator up top. X squared, because this is x and this is x, so x squared divided by what goes down here? 0.20 minus x, and that would be equal to Kb. And then what do we do next? What's the next step?
Set it equal.
Assume x is
Less than.
much less than 0.20. So therefore, 0.20 minus x will be approximately equal to 0.20. So that would simplify this to x squared over 0.20 is equal to Kb, which means that x would be equal to the square root of Kb times 0.20, which would be equal to the square root of 1.8 times 10 to the minus 5. Sorry, 5, not 4. Times 0.20. So let me see what that gives. 1.8 times 10 to the minus 5 times 0.2. And then I find the square root. So according to my calculation, this works out to be equal to, when rounded off to 2 sig figs, 1.9 times 10 to the minus 3. All right? M. Now this here is x, which would be equal to the concentration of OH minus. So that's what that's equal to. But the question is asking for the percent dissociation, right? Now, in the case of bases, the percent dissociation will be equal to the concentration of the OH minus divided by the initial concentration of the base. So in this case, the percent dissociation will be equal to 1.9 times 10 to the minus 3 m divided by the initial concentration of the base, which is 0.20 m, times 100%. And that would be equal to according to my calculation, that would be equal to 0.95%, which is obviously less than 5%. So the assumption we made would be valid as well. All right. Any questions about this one? Any questions? Any questions? Any questions? Yes, ma'am.
Sorry, could you explain the percent dissociation, like, with that problem? Can you like explain it like in the formula? Or
Okay, so remember I said, when this key is right here, for weak acids, right? The percent dissociation will be equal to the concentration of H plus divided by the concentration of the weak acid initially times 100%. All right, so this here is for weak acids, right? For weak bases, let me see if I can squeeze this here. For weak bases, the percent dissociation will be equal to the concentration of OH minus divided by the concentration initially of the base. So in this particular case, the base was this, right? The ammonium hydroxide times 100%. All right? So those are the separate formulas for calculating the percent dissociation of weak acids and weak bases. For weak acids, it's the concentration of H plus divided by the concentration of the acid initially, HA, times 100%. In the case of weak bases, it's the concentration of OH minus divided by the concentration of the weak base initially times 100%. And that's it. Right? Okay, any other questions about this? Going once, going twice. Okay, let me clear this. And let me scroll down to see if we can do any more. Okay, I'm going to leave 11A for you to attempt on your own because it's very similar to some questions we did before. Let me see, 11B. Okay. You won't be able to do 11B. Let me check 11C if there's one. Okay, so basically, let's scroll down and see what's happening. Okay, so you should be able to do A and D. You won't be able to do B and C. Not quite yet until I touch those topics. You should be able to do number 12 as well. And I think number 14 is a repeat, so you can ignore that. And you should be able to do number 15. Okay, so far, those are the ones you should try. What I just told you, I don't remember all of them right now, but you should be able to do the ones I just indicated. All right, so let me go back. What time is it? Okay, let me go back to the PowerPoint here, and let's talk about the relationship between the Ka for a weak acid and the Kb for its conjugate base. All right, so if you remember, if you have a weak acid, to get from the weak acid to the conjugate base, what do? You remove a proton, right? So for example, if your weak acid is HA, if your weak acid is HA, then the conjugate base is A minus, right? So HA is an acid, A minus is a base, and therefore if the acid is weak, it will have a particular Ka value, and if the base is weak, it's going to have the conjugate base. If it's weak, it's going to have a particular Kb value, right? What we're going to be looking at is the relationship between the Ka of a weak acid and the Kb for the conjugate base. That's what we're going to discuss right now. So let me clear this. And let me start off with the equation for the dissociation of the weak acid. As you can see there, something we're all familiar with by now. HA will dissociate to form A minus and H plus. At the same time, oh, and by the way, that would have a particular Ka value, depending on, of course, what the weak acid is. In the case of the A minus, because it's a conjugate base, it can act as a base according to this equation. A minus plus water gives you OH minus and HA, right? And because it's a weak base, it will have its own Kb value, right? Now, what would be the result when we add these two equations together? Now, if you remember from from your Chem 1 class, you should remember that when you're adding two or more equations together, I think you did this when in the topic of thermochemistry, Hess's law. I don't know if you guys remember that from your Chem 1. When you add two or more equations together, those items that are common to both sides will cancel out, right? So if you inspect this equation here and this equation, you're going to see that the items that are common to both sides will be the A minus, right? A minus here and A minus here. And then the other item that will be common to both sides will be the HA here and the HA here, right? And what do we end up with? We end up with that as your net equation, H2O to give H plus and OH minus. And this should look familiar to you. We made this earlier in this chapter. This is basically the auto-ionization of water, for which the K value is Kw. So this begs the question, what's the relationship between Ka, Kb, and Kw? Well, if you recall from before, the previous chapter, where we dealt with equilibrium constants for equations that we add together, if you remember, when we add the equations together, then the resulting K value would be the product of the K values of the equations we add together, right? So what that means is that the Kw value will be the product of Ka times Kb, all right? So therefore, if you know the Ka for a weak acid, you can easily calculate the Kb for the conjugate base and vice versa, because the product of those two constants will be equal to Kw. All right? So that's an important equation which will become handy in future problems, right? Now, so therefore, if you need to find Ka, you divide Kw by Kb, and if you need to find Kb, you divide Kw by Ka, right? So that's basically how you can calculate Kb and Ka if you know the other value. Okay, so that's the relationship between Ka and Kb. And here we have a list which demonstrates that relationship, because in this list, we have the acids here in this column, right? And we have the conjugate bases in the next column. And we have the corresponding Ka values for the acids and Kb values for the bases. And I don't know if you can see the numbers clearly, but if you, and you can try this at home, if you multiply the Ka for each acid by the corresponding Kb for the conjugate base, you're going to get Kw, which is 1.0 times 10 to the minus 14. And that is true for every acid and its corresponding conjugate base without exception, all right? You'll notice that in the case of sulfuric acid, remember, sulfuric acid is a strong acid, which means that the first dissociation is very strong, which means that the Ka is basically infinity, very large. And over here, the conjugate base of that acid has a Kb value which is very small, almost zero. All right? So basically, there's kind of like an inverse relationship between Ka and Kb, right? Ka for the acid and the Kb for its conjugate base. The higher the Ka value, the lower will be the Kb value, and vice versa. So if the acid is strong, then the conjugate base will be weak, and vice versa, right? And that's because the product of those two values is equal to a constant, which is Kw. Another thing I should mention, going back to this equation right here, is that, hold on 1 minute. Okay, there's one thing, unfortunately, I did not have in this slide right here. So let me create another slide. And I probably need to save this and upload it into Canvas. So let me create another slide here, because there are two other terms which I don't think I've introduced to you quite yet. And this is called pKa. So remember, we talked about pH and pOH, right? pH is minus log of H plus concentration. pOH is minus log of OH minus concentration, right? Well, there is a thing called pKa, which is minus log of Ka, all right? And basically, as I said before, I think I said it earlier, Ka is a measure of the strength of a weak acid, right? Remember I said that the greater the Ka value, the greater would be the strength of the acid. Well, it turns out that because of this negative sign, the greater the Ka value, if Ka increases, that means pKa decreases, right? So for a strong acid, relatively speaking, a strong weak acid, the Ka value would be relatively large, which means that the pKa value will be relatively small, right? And then there's pKb for bases. So this is for acids, weak acids. pKa is for weak acids. And then for weak bases, we have pKb, which is equal to minus log of Kb. So in this case, just like in the case of weak acids, if Kb is large or if Kb increases, pKb will decrease, right? So the stronger the base, the greater would be the Kb value, which means that the lower would be the pKb value. So let me ask you a question. What do you think is the relationship between pKa and pKb? Now, let me remind you. Ka times Kb is equal to Kw. Remember we saw that from earlier, right? So based on this relationship, what do you think is the relationship between pKa and pKb? All right, let me give you a hint. What would happen if you find, oh, I'm sorry, go ahead.
You have to arrange the equation you have at the bottom and put it into the minus log, or is that wrong?
Okay, so basically,
Sorry. Like you're solving for K, you're
all
solving.
right, so if I get you right, what you're going to do is find the minus log of both sides. Okay, so let's do that. Minus log of Ka times Kb will be equal to minus log of Kw. Okay, so what next?
Distribute the log.
Okay, so if you distribute, and remember, logs is a very unique function. Let me remind you of something you should have learned in your algebra class. Remember this? Log of AB is equal to what?
Log of A plus log of B.
Log of A plus log of B. Very good. I'm impressed. Because usually students forget stuff from their math class by the time they reach general chemistry 2. So, how would we apply that to what we have here?
Negative log of Ka.
Log of Ka minus log of Kb equal to minus log of Kw. So minus log of Ka is equal to what? pKa plus minus log of Kb, which is equal to what? pKb. So basically, and this now, another thing I'm going to introduce to you, this would be pKw. So minus log of Kw is equal to pKw. And it turns out that because Kw is equal to 1.0 times 10 to the minus 14, pKw is equal to 14.00, right? So therefore, the relationship between pKa and pKb is pKa plus pKb is equal to 14.00, right? So this is one of those situations, again, where if you know one, you can easily calculate the other. If you know pKa, you can easily calculate pKb by subtracting pKa from 14 and vice versa, all right? So this is very important stuff, especially when we get to the next chapter. Okay, what time is it?
33.
Okay. All right. Let me see what's up next. So, okay. So let me see here. Okay. All right. Let me talk about the relationship between the strength of an acid and the structure, right? So we're going to start with binary acids first. Binary acids, as you may or may not know, are acids which contains hydrogen plus one other element, right? So what we're looking at here are some binary acids where the other element is from group 7. We have hydrofluoric, hydrochloric, hydrobromic, and hydroiodic acid. So of course, when they dissociate, if X represents the halogen, this is basically the equation for the dissociation of these acids, right? Now, it turns out that there's a relationship between the strength of the acid and the strength of the bond. So basically, what this is saying is that the stronger the HX bond, then the acid will be weaker, right? So there's very little tendency, if the bond is strong, there's very little tendency for the bond to break and produce the hydrogen ions. So based on that, we know that the strength of the bond decreases as you go down the group from HF to HCl to HBr to HI, right? So the strongest bond is between the H and the fluorine atom. So therefore, that would be the weakest of the acids in that group. And then as you go down, the strength of the acid increases. In fact, for the other acids, as we said before, they are considered to be, for all intents and purposes, to be strong acids, right? And that is true pretty much for every group. Group 7 is basically a demonstration of that, but that is true for group 8, no, not 8, I'm sorry, group 6A and 5A, and I think that's as far as we can go, maybe 7A, I'm sorry, maybe 4A, all right? So that is one trend that we observe. As you go down the group for binary acids, the acid becomes stronger as a result of the bond becoming weaker between the hydrogen and that element. Now, when it comes to oxyacids, there are a couple of things that you have to take into account in terms of predicting the acid strength. So, just to remind you, an oxyacid is basically an acid which contains oxygen bonded to hydrogen, all right? Or at least one oxygen bonded to a hydrogen atom. So this is basically a generalized representation of an oxyacid, right? You have hydrogen bonded to oxygen and oxygen bonded to some element, right? That element could be something like carbon, a non-metallic element, by the way. Carbon, nitrogen, phosphorus, sulfur, whatever, right? So, like any acid, when it dissociates, it forms H plus as a result of the breaking of this bond, right? So it comes down to the breaking or how strong this bond is, just as in the case of binary acids, right? So what factors will affect the strength of the bond? Well, the bond would have to be relatively polar, right? So the more polar the bond, the easier for it to break. And it will break if this atom, which is bonded to the oxygen, is very electronegative. So an atom like nitrogen or sulfur and so on. Or oxygen, I'm sorry, not oxygen. Z, the same atom, is in a high oxidation state, right? So the oxidation state could be +3, +4, whatever, all right? So these are the two factors that would affect the acidity of an oxyacids, right? So let's deal with the oxidation number, or I should say let's take into account the group that the Z would belong to if they have the same oxidation number, right? So basically what you're going to find in this case is that the acid strength would increase with increasing electronegativity, of Z. So if Z is equal to iodine, chlorine, or bromine, what you'll find is that everything else being the same, the chlorine would have a higher, or the acid containing chlorine would have a higher acidity. So if we compare chloric acid, which is what this is, to bromic acid, what you'll find is that this will be more acidic because chlorine is more electronegative compared to bromine, right? So therefore, because chlorine is more electronegative than bromine, that means that chloric acid would be a stronger acid compared to bromic acid. So everything else being the same, with the only difference between bromine and chlorine between these two molecules, by that difference alone, the chloric acid will be a stronger acid compared to bromic acid, all right? So that's one effect of an electronegative element that would have on the acidity of an oxyacid. Now, the other factor has to do with oxidation number, right? So if the central atom is the same, the Z, but the oxidation numbers will be different, then what you're going to find is that as the oxidation number increases, the acidity of the acid increases. So let's look at these examples, right? If you look at all these oxyacids, you'll see that what they have in common is chlorine bonded to oxygen, bonded to a hydrogen. We have that here, we have that here, we have that here, and we have that here. But the difference is that the chlorine in each case will be bonded to different oxygen atoms or different numbers of oxygen atoms, right? So this chlorine here is bonded only to this oxygen atom here. This chlorine here is bonded to this and this. This chlorine here is bonded to 3 oxygen atoms in addition to this one. And this chlorine is bonded to 2 here and here, which is also bonded to this oxygen, right? So basically what you do is compare to see the number of oxygen atoms bonded to the chlorine, and that is related to the oxidation number that the chlorine atom will have in each case, right? So in the case of hypochlorous acid, the oxidation number of chlorine is 1. In the case of chlorous acid, it's +3. In the case of chloric acid, it's +5. And in the case of perchloric acid, it's +7. So what you'll find is that the acidity will increase with the increasing number of oxygens, which corresponds to the increasing oxidation number. So as a result of that, we can predict that perchloric acid will be the strongest acid, followed by chloric, followed by followed by chlorous, and then hypochlorous acid. And that is due to the increasing oxidation numbers on the oxygens, all right? Okay, what time is it now? Okay, I think I'm gonna stop here. And we'll continue our discussion on tomorrow on acid-base properties of salts, and I think that will be the end of this chapter. Let me just say that what I plan to do is, somebody asked me this morning about your test on Thursday, so I'm just going to make it 2 chapters, which would be equilibrium and this chapter. And let me just check something out here. Okay, there's nothing much left in this chapter here. So basically, after completion of this chapter, your test will contain questions based on this chapter, all right? I'll say more about that tomorrow. Yeah, that's it. Also, for assignment 3, remember it's due midnight tonight, so I'll be looking out for it, all right? And for those of you, not many of you are in this position, but for those of you who have not turned in any assignment at all, you can still turn it in. We'll be deducting points only in fairness to those students who have turned in their assignments on time, right? So if you have not turned in any of the assignments in the past that are past due, you can still turn it in and get credit, but please note that you'll be losing some points, all right? And I think that's all the housekeeping notices I have, so. See you guys tomorrow. Oh, by the way, let me get those who came in late. Is Bassie here? Let me check. Is Bassie? Bassie is not here. Burke?
Here.
Okay. Dunlop?
Bossy is here. I'm on
Bossy?
Zoom.
Oh, yes, I see you. Okay. Irvin? Was here? Is here. Olano? And right. Okay. Okay, well,
Said don't do 11B and C, right? For homework.
right.
And that's cross off.
Yeah, that's a repeat. Yeah, that's a repeat. Yeah.
And then 15 and 16 on the other page. Leave that for.
Yeah, I'm gonna do, yeah, especially 16 is kind of challenging. So, yeah, don't do 16.
Oh, okay. 16, 17.
But let me see here. Yeah, you should be able to do 15.
Okay.
Yeah. Okay, what's up?
This is my lab that was yesterday.
Okay, all right.
I
I have a long question, you sure?
Okay.
Yeah.
All right.
So, when you got this equation, I guess I kind of get lost. So when you're finding the KB and K, that's only for like week.
Right, A for weak acids, KB for weak bases.
So I only use that formula, where you do KB or KA times the.
It should be KB. Should be KB.
Sorry.
Okay, so, right, so, okay,
The square.
so that is right. KB times 0.20, and that gives you, KB is 1.3 times 10 to the minus 5, so you put that here,
Let's do like
times 0.2,
4 or 5.
and that gives you 1.9 times 10 to the minus 3. Now you have to remember, this is the concentration of OH minus from here. You see what I'm saying?
Yeah, I'm trying to see the correlation.
Exactly. If you had done this for the acid like we did here, that would be the concentration of H plus. But because we're dealing with a base, the X here would be the concentration of OH minus. You see what I'm saying? So we take that, because the question is asking for the percent ionization. We take that concentration divided by the initial concentration of the base times 100%. And that gives you, where is it? Oh, you didn't write it down? Whatever that gives.
Yeah.
That would be, right, that would be the percent dissociation of the base.
Oh, okay, so.
Right, exactly, right.
So
These are the two formulas, right, so you'll be using this.
yeah, that's what you're
For,
explaining. when I
right,
just solved it.
exactly. This would be for the acid, which is what we did up here. Right, so this is the formula for the percent dissociation of the weak acid. This would be the formula for the percent dissociation of the weak base. Yes, ma'am.
Same thing almost, but then, so is that how you got the 3.4 times 10?
Okay, same thing, approximation, and then you get this, right? And we did the percent dissociation, where is it? No, that's not it. We did, there it is.
Oh, sorry.
We did the percent dissociation, 5.2%, that's greater than 5%. So
Okay.
that means that we have to go back to this equation and do it the long way to get the quadratic. And then you get your X values. This one being positive would be the one that you'd use. So therefore, that would be equal to the concentration of H plus.
I'm sorry to cut you off.
Yeah, no
I know
problem.
you said it earlier too. Why again, if it's like greater than?
Because if
5%,
it's
do we have
great,
to do the long?
right, because if the percent dissociation is greater than 5.2%, that means that the approximation is not good. That means that,
Okay, so you're gonna get two different values. That's what you
right,
meant,
exactly.
right?
Now, in this case, we actually got the same value. It just so happened, right, no, it's actually the same. 0.0034 is the same thing as,
Oh,
Right.
okay, you might get different values here from here. Oh, I'm
exactly.
thinking
It
because-
just so happens that
Oh,
in
okay.
this case, you got the same value, but that's not going to be true in all cases. So that's the reason why if the approximation of the percentage, I'm sorry, if the percent ionization is greater than 5%, you have to go the longer route to get the more accurate value.
Then another one, so then just quickly,
Yeah,
the
yeah.
homework, I guess you wanted us to do, which one did you see?
I don't remember, let me see here, what did I say?
What you were saying before, but you said something like 15.
You should be able to do
11, 15.
11, but the A, not the B part, not the C part, so you should be able to do A and D. A and D for 11. A and D for 11. And D. And you should be able to do 12. Skip 14 because that's a repeat of an earlier question. You should be able to do 15, but not 16. So 15 you should be able to do. I said 9A and 9B?
No.
What she said, I don't remember exactly what.
Yeah, 9A.
Thank you.
Mhm.
This is my lab is due tomorrow, I won't be here.
Mhm.
Have a good day.
Mhm.
So I just wanted to ask, the test is this Thursday,
Mhm.
so even though we haven't finished the entire chapter, we're gonna learn the rest of it tomorrow and then.
Yeah, to be perfectly honest, I'm reconsidering that, so I'll let you guys know by tomorrow. Because you see, I would prefer that you guys get your assignment back so that you can review, and I post the answer key so that you can review everything, so I'll let you know what I will decide. Yes, ma'am.
Do you have any study tips for studying for the test? Cause I didn't do so good on the first one, and I wanna make sure that like. Just any tips on retaining the information and, not really retaining, but tying everything together
Right.
with the application.
You know what? I wish you were in my office earlier because I was just explaining to one of your fellow students about that. Basically what I would do is basically review the assignment, the past test, and try to do as many questions from your text as possible.
From the textbook?
Yeah.
Okay,
So each of the chapters will have, at least 100 questions. I won't expect you to do all of them, but just try to do as many as you can. And also, just as important, come and see me.
okay,
But basically, like I told a student earlier, it's all, when it comes to these things, you have to practice a whole lot of questions. You have to, because when you, try questions on your own, you get to see certain patterns, you get to see, if you read the question carefully. Like, for example, in the test that I gave you guys, there was one question which talks about a first order reaction and it gives you some information and so on. So if I were to do a question like that, the first thing I would think about are the equations for the first order reaction. One for half-life and the other one for relating the concentration to time.
okay,
And then basically I would look at the question to see if I can identify the terms that I can plug into that equation to find what the question is asking for. But you see, that takes practice, just doing as many questions as you can. And that's basically the best way to do it,
okay,
So, and the textbook also is very good in terms of it has some worked examples as well. You can look through those as well, So it's just a matter of just doing a lot of practice and coming to me and see me will help a lot,
okay,
So that's the reason why I'm coming here so often, so that you guys can ask me any questions you want concerning, anything that you might have some difficulty with.
okay.
All right?
And you think, watching your YouTube? would
That's
probably
good.
help you?
I would highly recommend that too, because not only do I explain stuff in the YouTube videos, but I work some examples as well.
Okay,
So yeah, I would do that too.
thank you.
All right? Yes, sir.
Are you gonna be here, after in your office right now?
Not right now.
Okay,
I have to hit the road and I have to come back, but I don't know how long,
okay.
what I'm doing.
Because I still have to print out my new, chart for last lab,
Uh-huh.
and then the charts for, last lab as well. Can I turn in both of those labs then tomorrow?
Oh, yeah, sure. Yeah,
Won't credit, that's fine.
yeah, that's fine, that's
Okay.
fine. Yeah.
Have a good day.
All right, you too.